Now we are going to talk about piecewise-defined functions. So piecewise-defined functions are defined by different rules on different parts of their domain. The first one we've looked at so far is absolute value of x. Absolute value of x measures the distance of a number from 0. So if I move out 2 spaces to the right or 2 spaces to the left, it doesn't matter. I've moved out 2 spaces away from 0. So the absolute value of -2 is a positive 2 distant units away from 0. So that's what the absolute value does, is it takes anything and makes it positive. So the easiest way to break up absolute value is to say that if it is already positive, which would mean that the x is greater than or equal to 0, if it's positive or 0, leave it alone, it's just x. Well, that's a line with a slope of positive 1 that goes through the origin, comparing to the y equals mx plus b form. Here my m is 1 and the b is 0, and that makes the line y equals x, a line with a slope of 1 and a y-intercept at 0. So if it's already positive or 0, leave it alone. But if it's not, if it's negative, if it's less than 0, it would be negative. Put another negative on it, and that'll turn it positive. Well, y equals negative x, again comparing here, would have a slope of -1 and a y-intercept at 0. So this is a line with a slope of -1 and a y-intercept at 0. So on this portion of the domain, when x is bigger than 0, we look like the line y equals x. And on this portion of the domain, when x is less than 0, we look like the line y equals -x. Here's another example of a piecewise-defined function. When x is less than 0, we behave like the line y equals x plus 2. And when x is bigger than 0, it behaves like the line the parabola y equals 1/2 x squared. So to evaluate f of -3, I would say -3 is less than 0. That's a true statement, so I plug in here. This would be -3 plus 2, so -1. Notice I do not plug in here because -3 is not on this portion of the domain. To evaluate f equals 0, I say 0 is less than or equal to 0. That's a true statement. So again, I plug into the top equation. I don't do the bottom. But for the x being a 3, 3 is not less than 0, but 3 is bigger than 0. So I plug in here. I do not plug into the top equation. I only plug into the bottom equation and get 9/2. So let's sketch that graph. So what we're going to do is we're going to plot a bunch of points like the ones we just plotted. At -3, 1, 2, 3, we're at -1, so we plot a point there. At 0, we're at 2, plot a point there. And at 3, we're at 9/2. So 9/2 is 4.5. So 4.5 would be about there. Okay, so x plus 2 is a line with a slope of +1 and a y-intercept at 2. That's this. So drawing that line with a slope of 2, notice I go down 2 and right 1. I'm sorry, a slope of 1, I'd go down 1, right 1, down 1, right 1. So I'd intersect right here. So this line is this line. Now, 1/2 x squared is a parabola. It's a parabola with its vertex at the origin. So I do not have an equal to on 0, so I put a open circle, whereas this one's a closed circle because I do have the equal to on 0. And then draw a parabola up through the point that we plotted. So my piecewise function looks something like this. So here's A, we already evaluated it. B, we evaluated it. C, we evaluated it. And then our graph looks something like this. This is what we just drew. So again, we just draw it one piece at a time. All right. Now, I want to sketch this graph. So when we're less than 2, it's the line y equals x plus 1, which is a line with a slope of 1 and a y-intercept at 1. Between 2 and 4, it's the constant function y equals 3, so that's a horizontal line. And then bigger than 4, it's the line y equals negative 2x plus 7. That has a slope of negative 2 and a y-intercept at 7. And also pay attention to where the closed circles are and where the open circles are. All right, so let's look at the graph here. So a line with a slope of positive 1 and a y-intercept at 1 up until 2. And then we put a closed circle at the end of that line. Then the constant function 3, we start with an open circle, but an open circle over a closed circle is just a closed circle. Constant function, so a horizontal line until we get to 3, we close it with a closed circle. And then negative 2, so a slope of negative 2, we put an open circle, y-intercept at 7, so we can either count it down or just start at 4 by plugging 4 in here. Negative 2 times 4 is negative 8, plus 7 is negative 1, so the point 4, negative 1. Then draw with a line with a slope of negative 2, so I go down to right 1 and plot my next point. Keep going. So my graph looks like this. All right, now I want to come up with a formula for this graph. Now notice over here, first of all, notice that it changes at 1. So I know I'm going to have two things, when x is less than 1 and something else when x is bigger than 1. Now, this has a closed circle on it for the less than part. So I'm going to draw the equal to there. This has an open circle, so it should not have an equal to. Now this is a line. Now notice we go through these points, so we have a slope of positive 1 here. So 1 in front of the x, and then plus the y-intercept. Well, my y-intercept is at 0, so it's just y equals x. And then this one has a slope of negative 1. Oh, I put that in the wrong place, didn't I? That was up here. Sorry. This one has a slope of negative 1, so a negative in front of the x. And now notice if I kept going up, I'd have a y-intercept at 3, so negative x plus 3. So our equation then, and here you can pause here and read this if you'd like, it gives more detail, is x when x is less than or equal to 1, or negative x plus 3 when x is bigger than 1. That's exactly what we drew.